Hello, and welcome to this presentation on number system conversions. This is part 2 of the presentation. In this presentation we'll be looking at the denary, the binary, the octal and hexadecimal systems. This presentation does assume you've seen part 1 of the number systems conversions presentation. Presentation overview. In the previous part 1 of the presentation we looked at conversions of binary to denary and denary to binary. In this presentation, part 2, we're going to convert denary to binary via the base of octal. We're going to convert binary to denary via the base of octal. We're going to convert binary to hexadecimal and convert hexadecimal to binary. Here are some definitions reviewed in part 1 of the presentation and stated here for reference. Conversion of denary to binary via the base of octal. For denary integers consisting of several digits, the process of repeatedly dividing by 2 can be quite lengthy as shown on the previous slides. In this case, it's generally easier to convert a denary number to a binary number via the octal numbering system. The octal system has a radix of 8, employing the digits 0, 1, 2, 3, 4, 5, 6 and 7. Example 1c. We're going to convert the octal number of 4316 base 8 to a denary number, to base 10. So looking at the octal system and using the column heading format, we would now have to the left of the decimal point 8 to the 0, which is 1, 8 to the 1, which is 8, 8 to the 2, which is 64, 8 to the 3, which is 512, 8 to the 4, 4096, and 8 to the 5, 32,768. You can check those values on your calculator. To the right of the decimal point in the octal system we would have 8 to the minus 1, which is 1 upon 8 or 0.125, 8 to the minus 2, which is 1 upon 8 squared or 0.015625. Now given the integer number of 4316 in octal, using the column headings we can work out the value in the denary system. So looking at the columns above, we get 4 times 8 to the 3, so that's 4 times 512, plus 3 times 8 squared, so that's plus 3 times 64, plus 1 times 8 to the 1, so that's 1 times 8, plus 6 times 8 to the 0, so that's 6 times 1. So adding up the numbers, we find that the number 4316 in base 8 is equal to 2254 in base 10, or in decimal. Again, we can write this as 4316 suffix 8 is equal to 2254 suffix 10, but the suffix 10 is optional. Now to go the other way and take an integer denary number, we can convert this into the corresponding octal number by repeatedly dividing by 8 and noting the remainder at each stage. This process will be shown on the following slide. Example 2c. We're asked to change the denary number 482.4375 into the corresponding octal number. We're going to undertake this in 2 stages. We're first going to take the integer part of our denary number and convert that into octal, and then we'll take the fractional part of our denary number and convert that into octal. So taking the integer part first of all, we're going to repeatedly divide it by 8 to convert it from denary to octal. So 8 divided into the 482 integer number, that goes 60 times completely, in other words 8 times 60 is 480, and we get a remainder of 2. So we write the 2 under the column heading of 8 to the 0. We continue our division process. We now divide 8s into 60, that goes completely 7 times because 8 7s are 56, and we get a remainder of 4. We write the 4 under the column heading of 8 to the 1. Continue our division process. 8s into 7 do not go, so we get a remainder now of 7. We write 7 under the column heading of 8 to the 2. So our octal number is 742. So in essence, 482 in base 10 can be written as 742 in base 8. Example 2c continued. We're now considering the fractional part of a number, and we're going to repeatedly multiply it by 8 and use the integers to form the octal number. So given a fractional number of 0.4375 on the previous slide, we multiply that by 8. It gives us a value of 3.5. We write the integer 3 under the column heading of 8 to the minus 1. We carry over the 0.5 and we multiply that by 8. That gives us a value of 4.0. We write the integer 4 under the column heading of 8 to the minus 2. That gives us an octal number of 0.34. Thus, 0.4375 in denary is equal to 0.34 in octal. So now bringing together the solution on the previous slide for the integer part of the number with the solution for the fractional part on this slide, we can write that 482.4375 in base 10 is equivalent to 742.34 in octal. Continuing the denary to binary conversion via octal, the natural binary code for the digits of 0 to 7 shown in the table and an octal number can be converted to a binary number by simply writing down the 3 bits corresponding to the octal digit. So what you'll see in table 1 here is we have the octal base from 0 to 7 and the equivalent binary number from the 0 to 111. And we're going to use this table to simplify the process of converting a denary number to a binary number. This will be shown on the following slides. Example 3c. We're asked to convert 2 octal numbers into binary numbers using the table 1. So given the octal number of 436, base 8, so 4 in octal on table 1 is actually written as 100 in binary. So we can replace the 4 octal with the binary number 100. 3 in octal on table 1 is written as 011 in binary. So we can replace the 3 with 011. And the number 6 in octal in our table is equivalent to 110 in binary. So we can replace the 6 with 110 in binary. So we can simply write down the conversion of 436 in base 8 as 100, 011, 110 in binary. All done using table 1. So the second number in example 3c to convert is 26.34 in octal. We've got to convert that to binary. So again, reading from the table, 2 in octal is 010 in binary, 6 in octal is 110 in binary, 3 in octal is 011 in binary, and 4 in octal is 100 in binary, all read from table 1. So we can immediately write down the conversion. 26.34 in octal is, in binary, 010.010100 in base 2. Just notice for reference that the 0 at the extreme left of the number can be omitted as it doesn't signify a number. So again, quite a straightforward process to convert from octal to binary using the table 1. So 5613 in base 10 is written as 12755 in octal. Here are some tutorial exercises I would strongly encourage you to attempt. Exercise 1c wants you to convert the number 3714 in base 10 into a binary number via octal. So in this case you will repeatedly divide the 3714 by 8, get an octal number, and then from table 1 we'll write down the binary number. The answers are given in the square brackets here. Exercise 2c wants you to convert the fractional number 0.59375 in base 10 to the equivalent binary number via octal. So in this case you will continually multiply the number by 8, reading the integer values as the octal number, and once you've got the octal number again using table 1 you'll be able to write down the binary number. Exercise 3C wants you to convert the real number of 5613.90625 in base 10 to a binary number via octal. So again, that will be involving the process involved in exercise 1C and 2C here to work out this real number conversion. And exercise 4C is giving you a binary number and it wants you to convert that into a denary number via octal. That will be reversing the process. So breaking the binary number down into 3 digits, you can write it immediately into an octal number, and then using the column heading method, you can write the octal number into a denary number. I would encourage you to stop the presentation here and attempt these exercises, but full work solutions are shown on the following slides. Exercise 1C solutions. We're asked to convert 3714 in base 10 into a binary number via octal. So the first thing we need to do is to take the 3714, repeatedly divide it by 8, looking at the remainders that form the octal number, which should be 7202 in octal. So to convert the 7020 in octal to binary, we simply use table 1. So 7 in octal from table 1 is 111 in binary, so we just simply write 111. So 2 in octal from our table gives us 010 in binary. 0 in octal is 000 in binary, and 2, as we said before, is 010 in binary. So in other words, 3714 in base 10 is written as 111 010 000 010 in binary. Exercise 2C, we're asked to convert 0.59375 in base 10 to the equivalent binary number via octal. So in this case, we take the fractional number given us 2 in decimal and continually multiply it by 8, reading the integer numbers as the octal number. Once we've converted the denary number into octal, again we'll go back to our table to write down the binary number. So number 4 in octal is 100, the number 6 in octal is 110. So we can write the decimal number of 0.59375 base 10 as 0.10011 in base 2. Exercise 3C, we're asked to convert the real number of 5613.90625 in decimal into binary via octal. So the first thing to do is to take the integer part of our number, the 5613, and continually divide it by 8, reading the remainders as the octal number. I'll let you go through the process, but the octal number should be 12755. So 5613 in base 10 is written as 12755 in octal. Exercise 3C continued. We now take the fractional part of the number given in the question in base 10 and continually multiply that by 8 and read the integer values as the octal number. That should give us 0.72 in octal. So 0.90625 in base 10 is equal to 0.72 in octal. So finally, to convert the 12755.72 in octal to a binary number, we simply use table 1. So from table 1, on the right hand side, 1 in octal is 001 in binary, 2 in octal is 010 in binary, 7 in octal 111, binary, 5 in octal 101 in binary, 5 again 101 in binary, point, and then 7 in octal is 111 in binary, and 2 in octal is 010 in binary. So we can now write down our final solution. So 5613.90625 in base 10 can be written as, notice I've omitted the 00 from the left hand end here. So I write 1, 010, 111, 101, 101 point, 11101 in base 2. I'd encourage you to check that solution for yourself. Exercise 4C, we're asked to convert the binary number of 11110 011.10001 space 2 to a denary number via octal. So initially we're going to write the binary number into octal using table 1. And just think of there being a 0 in front of the 1 here, if that helps you with the understanding of what follows. So taking 0, 1, 1 in binary on our table, 0, 1, 1 gives us 3 in octal, so I get 3 in octal. Looking at 1, 1, 0 in our table, that's 6 in octal. 0, 1, 1 in the table for binary gives us 3 for octal, and its point. 1, 0, 0 in our table for binary gives us 4 in octal, and 0, 1, 0 for binary in the table gives us 2 in octal. So we can now write the binary number in terms of octal, and it's 363.42 base 8. Now simply to convert from base 8 into denary, we use the column header method. So don't forget we're using the column headers here for the octal system. So we've got 8 to the 0, 8 to the 1, 8 to the 2, 8 to the minus 1, 8 to the minus 2. The process here is very similar to what we've done on the previous slides, so I'll let you wander through the process of converting the octal number into decimal. So eventually we find that given the binary number in the question, we can write it as a denary number base 10. Here are some tutorial questions to attempt. The first 3 questions wants us to convert the given decimal numbers, denary numbers, into binary numbers using octal. The solutions are given in the square brackets. And in question 4, we're asked to convert binary numbers into denary numbers via octal. Again, the answers are shown in the square brackets. I'd encourage you to stop the presentation and attempt those questions now. Hexadecimal numbers. Due to the complexity of computers, we require higher order numbering systems such as octal, base 8 we've already looked at, and hexadecimal, base 16 we're about to look at. The hexadecimal numbering system has a radix of 16 and uses the following 16 digits. So in hexadecimal, base 16, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which equate to the same in the denary system. But then we have A in hexadecimal equates to 10 in denary, B in hex is 11 in denary, C is 12, D is 13, E is 14, and F is 15. So that's the range of our hexadecimal numbering and its comparison with the denary system. Conversion of hexadecimal to decimal. Example 1D. We're asked to change the hexadecimal number, 2b, into a denary number. We're going to use the column header method for this. So as we're looking at now the hexadecimal system, the column headings to the left of the decimal point will be 16 to the 0, that will be units, 16 to the 1, that will be 16s, 16 to the 2, that's the 256s, and 16 to the 3, the 4096s. To the right of the decimal point, the fractional headings will be 16 to the minus 1, that's 1 upon 16, 16 to the minus 2, that's 1 upon 16 squared, or 1 upon 256. So in the question we're given the hexadecimal number of 2b, base 16, so that will be 2 16s and b, which is equivalent to 11 16s to the 0, or units. So 2b to the 16 will be 2 times 16 to the 1, plus 11 times 16 to the 0 from the above table, or it's basically 2 times 16 plus 11 times 1. So therefore 2b in hexadecimal is 43 in decimal, or 2b base 16 is equal to 43 in base 10. Example 2D, we're asked to convert the hexadecimal number 1AF to the denary system. So using the hexadecimal system, our heading columns now will be 16 to the 0, which will be the unit column, 16 to the 1, which will be the 16s column, and 16 to the 2, the 256 column. So writing the hexadecimal number in the columns, that becomes 1A, which note is equivalent to 10 in denary, and F is equivalent to 15 in denary. So doing the evaluation on this, 1AF is equal to 1 times 16 squared plus 10 for the A times 16 to the 1 plus 15 for the F times 16 to the 0. That gives us 1 times 256 plus 10 times 16 plus 15 times 1. So 1 AF in hexadecimal is equivalent to 431 in decimal. Answer is given here in the bases. Here are some tutorial exercises related to conversion of hexadecimal to decimal. In exercise 1D, you're asked to convert the B9 in base 16 to base 10. Exercise 2D, you're asked to convert CA in base 16 to the equivalent decimal, base 10. Exercise 3D, you're asked to convert the hexadecimal number 1E5D, base 16, to base 10. And exercise 4D, you're asked to multiply the hexadecimal number by another hexadecimal number, stating the answer in base 10. Again, I would encourage you to work out both the hexadecimal numbers in terms of denary numbers and then multiply them together. Answers are shown in the square brackets on the right hand side. Exercise 1D solution, we're asked to convert the hexadecimal number B9 base 16 into denary. I'm going to use the column header method to do that. I'll let you review the solution shown here. You should find that B9 base 16 is equal to 185 in base 10. Exercise 2D solution shown here, we're asked to convert CA base 16 into a decimal number. I'll let you review the solution that's shown here. Exercise 3D, convert the hexadecimal number 1E5D base 16 to base 10. Solution shown here. Exercise 4D, we're asked to multiply two hexadecimal numbers, two base 16 numbers together, and give the answer in terms of base 10. First step, take the first hexadecimal number given in the question and convert that using the column header method into decimal. So you should find the answer is given here for the first number. Exercise 4D continued, part 2. Second hexadecimal number given in the question, again converted using the column header method into a decimal number. You can check the solution here. And then finally we're asked to multiply the two numbers together to give the answer in denary form, decimal form. So this is the final answer. I'll let you check the solution for yourselves. Conversion of decimal to hexadecimal. So this conversion is undertaken by repeatedly dividing, this time by 16, and noting the remainder in each case. Example 1e, we're asked to convert 27 to base 10 into a hexadecimal number. This is an integer number, so we're going to take the integer part and repeatedly divide it by 16, noting the remainders to give us the hex number. So 27 divided by 16, 16 goes into 27 once completely with a remainder of 11. We write the 11 under the column heading 16 to the naught, noting that 11 in hex is actually B. Now divide 16 into 1, that goes 0 times, so we get a remainder of 1. We write the remainder under the column heading of 16 to the 1. That's 1 in this case. So 1b is our solution, our hex number, so 27 in base 10 is equivalent to 1b base 16. Example 2e, we're asked to convert the decimal number 547 into a hex number. Again, taking the integer part and repeatedly dividing by 16. So 16 into 547 goes exactly 34 times. You check that on your calculator with 3 remaining. We write the 3 under the column heading of 16 to the naught. Continue the process. 16 into 34 goes 2 with 2 remaining. 2 times 16 is 32, so we get a 2 remaining. We write the 2 under the column heading of 16 to the 1. Continue the process. 16 into 2 doesn't go, so we've got a remainder of 2, so we write that 2 under the column heading of 16 squared. So our hex number is 223. So 547 in base 10 is equivalent to 223 in base 16. Here are some tutorial exercises to attempt on conversion of decimal to hexadecimal. In question 1e, you've got to convert 48 in base 10 to base 16. Question 2e, 204 in base 10 to base 16. Question 3e, convert the denary number 182 to the hex number. And exercise 4e, convert the decimal number 329 into base 16. Answers are given in the square brackets on the right hand side. I'd encourage you to stop the presentation now and attempt the exercises. Decimal to hexadecimal conversions, exercise 1e. We're asked to convert 48 in base 10 to base 16. As we're given an integer in base 10, we'll repeatedly divide by 16. So it will be 48 divided by 16. It gives us 3 times exactly with no remainder. So we write 0 under the 16 to the power 0 column. And then 16 to 3 does not go, so the remainder is 3, so that becomes 3 written under the 16 to the 1 column. So 48 in base 10 is 30 in base 16. Exercise 2e, we're asked to convert 204 in base 10 to hexadecimal. Again, it's an integer, so we'll repeatedly divide by 16. So 16 to 204 goes 12. With remainder 12 in this case, and don't forget 12 in hexadecimal is equivalent to C, so we write C under the 16 to 0 heading. 16 to 12 doesn't go, so that's 0, but we've got a remainder 12, don't forget again 12 is C in hexadecimal, so we write C under the heading of 16 to the 1. So 204 in base 10 is CC in base 16. Exercise 3e, we're asked to convert the denary number of 182 into hexadecimal number. I'll let you look at the solution. The answer is given here. Exercise 4e, we're asked to convert the decimal number 329 into the base of 16. I'll let you review the solution here, and the answer is given at the bottom of the page. Table 2 shown on this slide is a comparison between decimal, binary, octal and hexadecimal bases. We'll be using this for reference in the following slides. So decimal base 10, binary base 2, octal base 8 and hexadecimal base 16. We go from 0 in decimal up to 32 in decimal, and then the equivalents in binary, octal and hexadecimal. Conversion of binary numbers to hexadecimal. What we're going to do here is arrange the binary bits in groups of 4 commencing from right to left, and then we're going to read the hexadecimal numbers from the table on the previous slide. So for example, given the binary number 11100 1111 0101 100, we're initially going to group it in 4s and then refer to table 2 on the previous slide. Example 1f. We're asked to convert the binary number given here into hexadecimal. So what we're going to do is break the binary number down into groups of 4. So we'll have a group here, we will have a group here, and a group here. Okay, so there's our 4 groups of 4 in this case. And all we're going to do is write the binary group down and then look up in the table on the previous page what the equivalent hexadecimal notation is. So taking the first group, the 1110, we go to table 2 on the previous slide, and for 1110 in the binary column, we see that is E in the hexadecimal numbering system. So we simply replace that with an E for hex. Looking at the next 4-digit group, we've got 0111. So again, back to our table 2, and 0111 is 7 in hex. So we simply replace the 0111 with 7. Our next group is 1010. So back to our table. So 1010 in the binary column is A in hex. So we simply replace that with A. And our final group of 4 digits is 1100, so back to our table 1100 in the binary column is C in hex. So we simply replace that with C. So now our binary number that's given to us in base 2 can be written as E7AC in hex. Conversion of binary numbers into hexadecimal. Some exercises for you to attempt here. Exercise 1F, we're asked to convert the binary number given here into base 16 into hex. Now just be careful, we have to break this down into groups of 4, so we will put a group of 4 here. So we'll have 1101 and 0110 as our two groups of 4 there. Exercise 2F, we're asked to convert this binary number again into a hexadecimal number, and again be careful with the way we format the groups. We will have a group of 4 broken here, and effectively we'll have a 0 in front of this group here to make it into a group of 4 there. Just be careful of that. So we'll have a 0110 group and a 0111 group when we do the conversions. I'll leave you with exercise 3F and 4S to review. It's similar kind of problems to 1 and 2. Conversion of binary numbers to hex. These are the solutions. So exercise 1F solution given here for you. I'll let you look at that on your own. Answers are given here. Exercise 2F, as I said in the previous slide, make sure you put the 0 in front of the 4 digits for the first term there. So 0110 you look up in your table. But again, I'll let you review the solution to that problem. Exercise 3F and exercise 4F solutions given here. I'll let you review them in your own time. They all relate to the table 2. The conversion of hexadecimal numbers to binary numbers. So to convert from hex to binary, we simply reverse the process shown on the previous slides. So example 1G, we're asked to convert the hex number 5CF4 to binary. So breaking that down, first of all we take the number 5 in the hex system, we go to our table 2, we look up 5 in hex and read off on the binary column of 0101. So we write down 0101 for the 5. Taking the next hex number is C, so on our table, if we go and look at C in the hex column and read off the equivalent binary number, it's 1100. So we simply place a C with 1100. Looking at the F in table 2, F in hex is equal to 1111 in binary, so we simply replace the F with the 1111 in the binary system. And finally 4 in hex, looking at 4 in the hex column, hexadecimal column, reading off the binary, we get 0100. So we replace the 4 with 0100. Putting them all together, we get 101, 1100, 1111 and 0100 in base 2. Notice I omitted the leading 0 in the binary number as it doesn't signify a value. I would encourage you to have a go at the exercises given here. Exercise 1G, you're given a hex number to convert into base 2 into a binary number. In questions 2G, 3G and 4G are all very similar. Answers are shown in the square brackets on the right hand side. Again, refer to table 2 in your solutions of these exercises. So conversions of hexadecimal numbers to binary using table 2. Exercise 1G, we're asked to convert 3F in base 16 to binary base 2. Don't forget we're simply using the table 2 on the previous slide. I've just shown an extract of it here on the right hand side for convenience. So in hexadecimal we're looking for 3. So 3 in hex is 0011 in decimal, so that's the first part of the number. And then F in hex, going down our columns here, F is 1111 in binary. So the solution is 3F in base 16 is 111111 in base 2. Notice again I've omitted the 2 leading zeros here as they have no significance in their value. And with exercise 2G, we're given a hex number of A6 to convert it to binary. What we do again on our table is look at the value of A in hex and read off the binary equivalent. So A is 1010, and then look at the value of 6 in hex, which in binary is 0110, so 0110. So A6 in hex is written as 1010, 0110 in base 2. Conversions of hex to binary continued here. Exercise 3G, you're given 7b in base 16, convert to base 2. I'll let you look at the solution here. And exercise 4G, you're given 17d in base 16, convert to binary. Again, solution is given here for you. I'll leave you with some tutorial questions to attempt. In question 1, you're asked to convert hexadecimal numbers into their decimal equivalents. In question 2, you're asked to convert decimal numbers into their hexadecimal equivalent. In question 3, you're asked to convert binary numbers into their hex equivalent. In question 4, you're asked to convert hex numbers into their binary equivalent. Answers are shown against each question in the square brackets. So in summary, to convert any base to denary, we always use the column method. To convert denary to any base, we continually divide the integer part by the base, and we note the remainders at each stage, and we continually multiply the decimal part by the base, noting the integers at each stage. To convert from denary to binary via octal, we first divide the denary number by 8 to get the octal number, and then convert the octal number into a 3-digit binary number using table 1. To convert from binary to denary via octal, we convert the binary number to octal using table 1, and then use the octal column method to convert the number into a denary number. To convert a binary number to hexadecimal, we split the binary number into groups of 4 and then use table 2 to directly write down the hexadecimal number. To convert the hexadecimal number to binary, for each hexadecimal number we just convert it to the equivalent binary number using table 2. Here's the bibliography used to help create this presentation, and again I would encourage you to look at the reference sources. Some are very good here, good background information to the presentation we've outlined here. I hope this presentation has been of help to you, and thank you for viewing.